Hello everyone, welcome to Principles of Communication System lecture series. In this video, we are going to discuss about introduction to noise, short noise and white noise. Noise. In any communication system, during the transmission of the signal or while receiving the signal, some unwanted signal gets introduced into the communication, making it unpleasant for the receiver, the questioning the quality of the communication. Such a disturbance is called as a noise. What exactly noise is? Noise is an unwanted signal. Noise is an unwanted signal which interference with the original message signal and corrupts the parameter of the message signal. This alteration in the communication process leads to the message getting altered. It most likely enters at the channel or the receiver. The noise signal can be understood by taking a look at the following figure. So this is the amplitude of the signal and this is the time of the signal. So this is the noise signal. Noise signal is the random in its nature. So this is the irregular signal. So is amplitude characteristic is in random nature. It varies from minimum to maximum and minimum to medium, medium to minimum. So nature is irregular. Hence, hence, it is understood that the noise is some signal which has no pattern and no constant frequency or amplitude. It is quite random and unpredictable. Measures are usually taken to reduce it, though it can't be completely eliminated. So these are some common examples of the noise. The common noises are is sound in radio receiver, buzz sound of telephone conversation, flicker in television receiver. So these are some common examples of the noises. Now we will look into some classification of the noise. Noise we classified into two types. The first one is external noise and second is internal noise. The external noise is further classified into two types: man-made noise or industrial noise and natural noise. The natural noise is further classified into two types: atmospheric noise and extraterrestrial noise. The extraterrestrial noise is further classified into two types: solar noise and cosmic noise. The internal noises are short noise, high frequency noise or transit time, low frequency noise or flicker noise, partition noise and thermal noise. So these are some types of noises. Short noise is one of the internal noise. Short noise is produced by random movement of electrons or holes across a amplifying device due to discontinuities. The short noise is produced due to a short effect. Due to the short effect, the short noise is produced in all the amplifying devices rather in all the active devices. It appears as a randomly varying noise current superimposed on the output. The short noise sounds like a shower of lead shots falling on a metal sheet. The short noise has the uniform spectrum density like thermal noise. The exact formula for the short noise can be obtained only for diodes. For all other devices, an approximate equation is stated. The mean square short noise Current for a diode is given as I subscript Sn square is equal to 2 into Q into I plus 2 I naught into B. Here I, so this is I is equal to direct current across the junction. The unit is amps. I naught I naught is the reverse saturation current in amps. So this is the I naught. So I naught is the reverse saturation current and I is the direct current across the junction. So junction is the diode junction. Q is the electron charge. Q is the electron charge is equal to 1.6 into 10 to the power minus 19 coulomb, and B is equal to effective noise bandwidth in hertz. And this is the formula for short noise. For the amplifying device, the short noise is inversely proportional to the transconductance of the device and is directly proportional to the output current. We will discuss short noise with some specific problem. The given problem is a noise generator using a diode is required to produce 15 microwatt noise voltage in a receiver which has a input impedance of 75 ohm purely resistive. The receiver has a noise power bandwidth of 200 kHz. Calculate the current through the diode. So here we have to find out the current through the diode. So they are given voltage VBN is equal to 15 microwatt. The 15 microwatt is the required noise voltage. So noise voltage is equal to 15 microvolt and given resistance is 75 ohm. So this is the given resistor value. It's equal to 75 ohm and noise power bandwidth is 200 kilohertz. 200 kilohertz. We have to find out the current through the diode. The first you list out the given datas. The given datas are VBN is equal to 15 microvolt, resistor R is equal to 75 ohm, and BN is equal to 200 kilohertz. We know that ISN square is equal to 2Q into I plus 2IS into BN. So this is the short noise equation. So since I is much greater than Is. So Is is the reverse saturation current is the negligible value. So in this condition you modify the original equation. So after modification Isn square is equal to 2Q into current I into bandwidth Bn. So Isn square is equal to 2Q into I into Bn. So now our intention is to find out the I. They are not given any ISN value. So we have to find out the ISN. So we know that I is equal to V divided by R. So with respect to noise, short noise, we have to find out the current. So ISN is equal to we know that I is equal to V divided by R. ISN is equal to VSN by R. So they are given VSN is equal to 15 microvolt and R is equal to 75. So we get ISN is equal to 0.2 microamps. So ISN is equal to 0.2 microamps. Now we have to find out the current I. So this is the current. So this is the equation. From the equation, so just you modify the equation. So I is equal to, you retain I as it is. I is equal to ISN square divided by 2Q into Bn. So now you substitute ISN value. ISN is equal to 0.2 microamps. This is ISN square is equal to 0.2 microamps whole square divided by 2 into Q. the Q is equal to 1.6 into 10 to the power minus 19, and Bn is the bandwidth. The given bandwidth is 200 kilohertz. So it's equal to 200 into 10 to the power 3. So simplify this. After simplification, so we get current is equal to 625 milliamps. So this is the current. 625 milliamps is the current through the diode. Low frequency or flicker noise is the internal noise. The flicker noise will appears at the frequency below a few kilohertz. It is sometimes called as a 1 by F noise. The power spectrum density of this noise is increases as the frequency is decreases. In the semiconductor devices, the flicker noise is generated due to the fluctuation in the carrier density. These fluctuation in the carrier density will cause the fluctuation in the conductivity of the material. This will produce a fluctuating voltage drop when the direct current flow through a device. The fluctuating voltage is called as a flicker noise voltage. So for example, you consider one transistor, the mean square value of the flicker noise voltage is proportional to the square of the direct current flow through the device. So here device is transistor. It is proportional to emitter current. So transistor emitter terminal current and junction temperature is inversely proportional to the frequency. High frequency or transit time noise is the internal noise. If the time taken by an electron to travel from the emitter to collector of a transistor become a comparable to a period of the signal which is being amplified, then the transit time effect take place. This effect is observed at very high frequencies. Due to the transit time effect, some of the carrier may diffuse back to the emitter. This gives rise to an input admittance, the conductance component of which increases with frequencies. The minute current induced in the input of the device by the random fluctuations in the output current will create random noise at high frequencies. This process gives rise to an admittance in which the conductance component increases with frequency. This conductance as a noise current source which is associated with it in parallel. This conductance is increases with frequency, the power spectrum density is increases. Once this noise appears, it goes increasing with the frequency at the rate of 6 dB per octave. White noise is one of the internal noise. The noise in an idealized form is known as a white noise. Thus, in a communication system, the noise analysis is based on an idealized form of noise, that is white noise. The white idealized form noise is known as white noise, or continuous noise is known as a white noise. Idealized form or continuous noise is known as a white noise. As white light consists of all color frequencies, in the same manner white noise contains all frequencies in equal amount. The power density spectrum of a white noise is independent of frequency. This means that the white noise consists of all the frequency component in equal amount. If the probability of the occurrence of a white noise is specified by a Gaussian distribution function, it is called as a white Gaussian noise. Since the power density spectrum of thermal and short noise is independent of the operating frequencies, therefore short noise and thermal noise can be treated as a white Gaussian noise for all practical purpose. The spectrum density of the white noise is expressed as Sn of f is equal to n0 by 2. So this is Sn of f is equal to n naught by 2 is the spectrum density of the white noise. Here, the factor 1 by 2 has been included to show that half of the power is associated with a positive frequencies and remaining off with the negative frequencies. This has been shown in this figure. So this is a power spectrum density diagram. This is n naught by 2. Half is associated with a positive and another half is associated with a negative. So n naught by 2 is indicate the spectrum density. The power spectrum density of a white noise shown in this above figure, it reveals the fact that it has no DC power. That is, the mean or average value of white noise is 0. In addition to this, the autocorrelation function of the power spectrum density of white noise may be obtained by simply taking the inverse Fourier transformer of the both side. So this is the power spectrum density. So Sn of f or S omega of omega is equal to n naught by 2. So now you simply take the inverse Fourier transformer on both side. So we get the power spectrum density of the white noise. The power spectral density of autocorrelation function form a Fourier transform pair. The Fourier transform of autocorrelation R of tau is equal to Sn of f. Sn of f is the power spectrum density of the white noise. So we have to find out the autocorrelation. So autocorrelation is R of tau. R of tau is equal to inverse Fourier transformer of Sn of f. So we know that Sn of f is the power spectrum density of the white noise is equal to n naught by 2. So R of tau is equal to inverse Fourier transformer of n naught by 2. So R of tau is equal to n naught by 2 into delta of t. So this is the autocorrelation form of Fourier pairs. So R of tau is equal to n naught by 2 into delta of t. So above is the expression for the autocorrelation function of white noise. The autocorrelation function can be plotted. So this is autocorrelation function plot. So vertical axis is R of tau and horizontal axis is tau R t. So spectrum density is equal to n naught by 2 into delta of t. So this is the autocorrelation function of a white noise. The correlation function is plotted. The vertical axis is R of tau and horizontal is tau. This is the spectrum. The spectrum is n naught by 2 into delta of tau or t. Thank you.